A while ago, I built this little breadboard computer, and now I want to connect an RS-232 serial interface to it. And these serial interfaces used to be ubiquitous on computers for connecting to modems and printers and mice and whatnot. But nowadays, everything's USB, and you typically need a USB adapter like this if you want an RS-232 port. But there still tend to be niche devices that use this serial interface, like this router that has a console port. This is actually a serial interface, and with the right adapter, we can connect this to a computer and use a serial terminal program to log in, configure, and troubleshoot this router using a basic text interface. And that's what I want to add to my breadboard computer, a serial connection that I can use to create a basic text interface like this. Now, it's called RS-232 because it was originally recommended standard 232 back when it was introduced in 1960, and that's still often how it's referred to, and I'll often call it that, but it's now officially called TIA-232, and if you want to read the actual standard, you can get your very own copy for just $156. Here's my copy, and as it turns out, much of what's in here isn't relevant to any modern or even any really widespread historical implementation of RS-232. For example, the standard requires this 25-pin connector, and while a 25-pin connector was common at one point, even then, most of the pins were unused. But the TIA-232 standard actually defines functions for almost all of the pins. Here are all of the pin functions for the 25-pin connector, and since most of these pins were never used widely, many manufacturers started using 9-pin serial connectors for cost savings. But it's sort of interesting to look at what the original standard contemplated. So of course you've got transmit data and receive data, as you'd expect. But in addition to that, the original standard had a secondary transmit data and secondary receive data. And in fact, if you look at some of the other control signals, there's secondary versions of those as well. And so the standard technically has an entire secondary data channel. So there's actually two separate serial interfaces on this connector. Another thing that's interesting is that RS-232 is generally notable for not including a clock. And you'll see more about that here in a minute. But it's interesting that the standard actually does include some clock signals here. And I've never seen these used, but it's just sort of interesting that they're included in the standard. And then finally, there's a couple extra pins for doing loopback testing. So there's some test functions. But as far as I know, none of these things were ever widely used. In fact, most of the signals on the 9-pin connectors aren't strictly necessary either, as you'll see. And that 9-pin connector was eventually standardized as TIA-574. Anyway, as the standard would suggest, RS-232 is an interface between data terminal equipment, or DTE, on one end, and data circuit terminating equipment, or DCE, on the other. The idea is you'd have a communication circuit of some sort. It could be a phone line, a leased line, something like that. And then on each end of the circuit, you'd have data circuit terminating equipment, or DCE. A common example of a DCE might be a modem. And then connected to the DCE is a computer, which is the data terminal equipment, or DTE. And then the RS-232 standard just covers what's going on physically and electrically between these two devices. But it's common to just ignore all of this other stuff and think of RS-232 as just a serial interface between any two devices. In my case, I've got this serial USB adapter connected to a laptop on one end running some terminal software. So this end is the DTE, data terminal equipment. So that makes the thing I want to connect it to, the 6502 breadboard computer over here, the DCE. And it's important because the different pins are defined as going in particular directions, like received data on pin 2 or transmitted data on pin 3. All these terms are defined by the standard from the perspective of the DTE. So transmitted data on pin 3 would be data transmitted by the DTE, or in my case, the laptop, and received by the DCE, or the breadboard computer. In fact, I can hook an oscilloscope up to pin 3 to see what data is transmitted. So pin 3 is transmit data, and then pin 5 is a signal ground. And so with transmit data and signal ground hooked up to the scope, let's take a look at what the voltage is across those pins when we connect this. So as soon as I connect it, I see that the voltage drops down to actually a negative value, because right here is ground, that's our reference value, and it drops down to a negative voltage. And if we go, let's see here, so this is 2 volts per division, so 2, 4, 6, maybe a little over 6 volts negative. So now if I pull up my terminal program and just start pressing some keys to try to transmit data, nothing shows up on the terminal. And that's because the receive data pin isn't hooked up to anything here. The terminal is only going to show data that's received by the DTE. But if I look at the scope while I'm transmitting data, we see there is actually data being transmitted, and the scope is seeing it as a voltage across those lines. So let's try to capture one of those. So if we do a single shot here, and then I just press a key, that transmits one character, and we can see it on the scope here. And so it's interesting to note that ground is right here, this right in the middle here. So the voltages we're seeing are either, negative 6 or 7 volts or like positive 7 volts. If we look at the standard under electrical characteristics, we can see that the signal shall be considered in the marking condition when the voltage is more negative than minus 3 volts, and it should be considered in the spacing condition when the voltage is more positive than 3 volts. And it says the region between plus and minus 3 volts as defined as the transition region, and the signal state is undefined. So we see here it's below negative 3 volts, and here it's above 3 volts positive. So the standard calls this the mark condition down here, and this is the space condition up here. And the terms mark and space actually come from the era of telegraphs and paper tape, where a mark would literally be a mark or a hole or something in the paper tape, and a space would be nothing or just a lack of a mark on the tape. But here the mark symbol is a negative voltage, which means a binary 1, and a space is represented by a positive voltage, which means a binary 0. So if we look at this, we can see it looks like it's sort of stuck in that 1 state, and then we get a 0 or maybe a couple zeros, and then a 1, and then some more zeros, and then a 1 or maybe a couple 1s, and then a 0 or a couple zeros. And it's actually kind of hard to know how many bits we've got, since I'm just kind of guessing that maybe that's 1 bit there. And that's actually a limitation of the way that RS-232 works. There is no separate clock to tell us where each bit is. You can compare that to some of the other protocols we've looked at on this channel. With SPI, there's a separate pin with a clock, and each positive transition of the clock tells you when to read a bit off the data line. Likewise, USB and Ethernet encode data in a way that you can recover the clock from the data signal. But with RS-232, there is no information encoded in this signal that tells us where each bit is. The only way to know is that both ends of the connection have to agree on the data rate. So in the computer where I'm transmitting, the terminal program has a setting for baud rate. And baud refers to symbols per second. So in this case, each bit is a symbol. So this is set to 9600 bits per second. And if we take 1 divided by 9600, that gets us about 1 bit every 104 microseconds. So if we set the scope to, let's say, 200 microseconds per division, then 104 microseconds will be about half of a division. So each of these divisions here will be about 2 bits. So just kind of eyeballing it here, it looks like we've got, so these are all 1s, and then we get 0, 0, 1, 0, 0, 0, 0, 1, 0, and then 1, and then it just stays as a 1 there. And I'm just kind of eyeballing 1 bit every 100 microseconds or so based on these tick marks, even though the bits are really being sent every 104 microseconds. Now, does that really matter? Well, eventually, yes, it does. So here's an illustration of the importance of having clocks synchronized between the transmitter and receiver. So the blue here represents some transmitted data, and it's just alternating bits 0, 1, 0, 1, 0, 1. And the red here indicates the receiver and its clock when it reads each bit. So as time progresses here, we can see the receiver reading each bit right on time. And so if the transmit clock is different, then you can see that kind of skews that data, but it can be actually quite a bit different here, and we'll still receive the same bit. And same thing for the receive clock. If the receive clock varies actually quite a bit from 9600, the receiver is still going to receive the same bit. But as we get out here further in time, so if we come out to one of these other bits out here to the right, you can see even a fairly small variation in the transmit clock will cause the receiver to miss that bit and read the wrong value. Similarly, any difference in the receiver's clock when it samples that bit can also cause it to read the wrong value. And of course, if both clocks are off by the same amount, it kind of cancels each other out and works out. But if one clock is a little fast, one clock's a little slow, we'll read the wrong bit. And you can see this is just after 45 bits, and I've still got a fairly big difference, but any difference whatsoever between the transmit clock and the receive clock will eventually cause a problem and cause some corrupted data, or what we call a clock slip. Now, some communication protocols handle this by requiring that both the sender and receiver have extremely precise timing, using atomic clocks or GPS clocks or something that's just guaranteed to be 100% accurate. But RS-232 doesn't require that. Instead, it uses the first bit to resynchronize the clocks for every byte that's sent. That way, as long as the clocks are close enough to line up for 10 bits or so, it's okay if they're not perfectly in sync. So if we look at what we've got here, the line is held at a negative voltage when it's idle. And then when I transmit a character, this first bit is this positive voltage here. And that's always how every character starts. The first bit is called a start bit, and the line goes positive for 1 bit time, which is half a division here. Then the next 8 bits just make up whatever byte is being transmitted. And it's sent least significant bit first, so we've got a 0, followed by a 1, 0, 0, 0, 0, followed by another 1, then a 0, like that. And this corresponds to a 4-2 in hex, which is the ASCII value for a capital B. And that is, in fact, the character I pressed when I transmitted this. It's a capital B. And then following that is at least 1 bit time where we're back at a negative voltage, and that's a stop bit. And so it'll stay low, or stay negative, I guess, for 1 bit time, and then either stay low like that, or after 1 bit time, it can go high again, or go positive again, I should say, as another start bit for the next character. And just like the data rate, all this has to be agreed to ahead of time. So here's a configuration for my terminal program, and we've got the data rate of 9600 bits per second. And there always has to be a start bit at the beginning of every character to synchronize the timing. But then we can actually configure the number of data bits. Now in our case, we've got 8 data bits, which is why I decoded it the way that I did with 8 bits. But we could set that to whatever we want as long as the transmitter and receiver agree on it. Then following the data bits, we have the option of including a parity bit. And you can check out my other videos on parity for more about how that works. But it's just an extra bit that gets sent for error detection that we can either ensure that there's an even number of ones, an odd number of ones, or apparently we can always have that extra parity bit set always to a mark or always to a space, always a 1 or always a 0. Kind of strange to use either of those options. But in our case, we're not sending a parity bit at all. And then we can set the number of stop bits at the end. And remember, the stop bit basically just translates into the minimum amount of idle time between characters. So in our case, just 1 bit time. So with this configuration, to send an entire character takes 10 bits. We've got the start bit, we've got 8 data bits, and then 1 stop bit. So at 9600 bits per second, that means we can send 960 characters per second. In a future video, I'll show you how to use some specialized chips that are designed for interfacing with RS-232. But for now, I'm just going to use a transistor to convert the signal we've got into a normal 5-volt logic signal. So here's the RS-232 signal coming in, and when it's a negative voltage over here, current would want to flow through the transistor from ground to the negative voltage. But the transistor is not going to allow that to happen, so no current's going to flow base to emitter, meaning the transistor is going to be turned off, and so this pin here would be floating, meaning that this resistor is going to pull the output to a plus 5 volts. But when the input over here is a positive voltage, then current can flow from that positive voltage from the base to emitter down to ground here, and current flowing through that will turn the transistor on, which will then pull the collector down to ground as well, pulling the output to 0 volts. So let's build that. Here's the transistor. I'll connect the emitter to ground. Then we have our input from the RS-232 transmit data pin going through a 10K resistor to the base. And the output's pulled high through another 10K resistor. With that connected, let's hook up the scope to see if it's working as we expect. So now I've got channel 1 connected to the RS-232 transmit data like before, and then channel 2 is connected to the output of the transistor. And we can see that, hang on, oh, we got a bad connection here. There we go. So we can see channel 1, the RS-232, is idle, sitting at a negative voltage like that. And if we look at channel 2, let's move that down here. There we go. Channel 1 will move up a little bit. So we can see channel 2. This is ground, and then each division is 5 volts, so we can see channel 2 sitting at plus 5 volts. Channel 1 is sitting at now a negative voltage. Now let me capture a character. Actually, let's single shot here. Capture a character, and that looks good. So the start bit is here, and the transistor turns on at that point, pulling this to ground. And then you can see our signal switches between ground and 5 volts, indicating either zeros or ones. Instead of a positive voltage and a negative voltage, we get 0 volts and 5 volts, indicating our zeros and ones. So that'll work perfectly to connect to one of the I/O pins on the 6522. So I'm going to connect it to bit 6 on port A here, and I'll talk about why in just a second. Now let's see if we can detect data coming in on that pin. I'll start with some code for the breadboard computer that just initializes the LCD screen, and I've got a routine in here for printing characters to it. So it was bit 6 on port A that we connected the transmit data line to, so let's set that bit to input. And the reason I chose bit 6 is because I can use the bit instruction to check for changes on that bit. So the bit test instruction sets the 0 flag based on ANDing the accumulator, but we don't care about that. What it also does is it sets the negative flag and the overflow flag rather, based on bits 7 and 6. So it'll basically just copy bit 6 here into the overflow flag. And so why do we care about that? Well, there's also this BVC and BVS, which will branch if the overflow flag is 0 or branch if the overflow flag is 1. So that makes it very easy for us to read that bit in to bit 6 using the bit instruction, and then branch either if it's set or if it's cleared. So we can easily create a loop waiting for a start bit. We just do a bit test on port A, which among other things puts port A bit 6 into the overflow flag. Then we can branch if overflow is set back to Rx wait. This will sit in a loop as long as the input signal is high, which it is while it's idle here. So we'll just keep looping until we get to the start bit. If we drop out of the loop, that means we're getting a character of data. So for now, let's just print an X on the screen and then loop back up to wait for the next character. So let's save this. We'll assemble it and write it to the EEPROM. There we go. I'll put the EEPROM back in and reset. And we're getting nothing but X's. So what's going on here? Did I do something wrong? Oh, I see what I did here. Okay, so this is I'm continuing this loop as long as the overflow flag is clear, but really I want to continue in the loop while the overflow flag is set. So BVS, branch while overflow is set, back to here to stay in this loop. Let's try that. Okay, let's try this one. So we'll put the EEPROM back in, get it aligned correctly, reset. Okay, so now it's not printing anything, but if I go to my terminal, I hit a key, we get some X's. And actually we get more than one X. So if I hit a key again, we get a few more X's. So it's detecting when it's receiving a bit, and I guess as long as it's getting zeros somewhere in there, it prints X's as fast as it can. So I guess that tells us we're getting something here. So now that we can detect that we're receiving something, let's try to decode what it is. So instead of just printing an X, let's create a loop to receive 8 bits. So we'll put an 8 into the X register, and then start a loop to read each bit. And after we read the bit, we'll decrement X, and then we'll branch if X is not equal to 0 back up to read bit. So whatever we put in here is going to be executed 8 times. So now to read each bit and assemble the full byte, we can again do a bit test for port A, which will put port A bit 6 into the overflow flag. But to assemble the byte, we need something like the rotate left or rotate right instruction. These instructions take the carry bit and shift it into the A register, shifting all of the bits in the A register over as well. In our case, since RS-232 sends the least significant bit first, we want rotate right, which will rotate the carry bit into bit 7. So the first bit we receive will eventually get rotated all the way over to bit 0, and the last bit we receive will end up as bit 7. So we'll do a rotate right here to rotate the A register right, putting the carry flag as the new most significant bit. The problem here is we just read the bit into the overflow flag here, but rotate right needs it in the carry flag. Unfortunately, I don't think there's an easy way to read it directly into the carry flag, so we'll need a little bit of if-then logic here. So after we read into the overflow flag, we can branch if overflow is set, which means we received a 1. So if we get to receive 1, we can set the carry flag because we read a 1, and so we want to put a 1 into the carry flag. Otherwise, we won't take this branch and we'll drop down here and we can clear the carry flag because we read a 0 and we want to put a 0 into the carry flag. And then after that, we need to skip down, so we'll jump to receive done, which is down here. Now when we get to the rotate right here, the carry flag will have whatever bit we just read, and it'll get rotated into the A register. And after we go through this loop 8 times, all 8 bits are now in the A register in the right order. So now we can call the print character subroutine to print the A register to the screen to show which character we received. And then of course we've got our jump back up to receive wait to start it all over and wait for receive the next character. And so this will read 8 bits into the A register and print out the result. The problem is that it reads the bits as fast as it can. It completely ignores the timing. So remember, at 9600 bits per second, we actually need to read the bits exactly every 104 microseconds, or at least pretty close to exactly that. But this code is reading it as fast as possible. So somewhere we need to add a delay, basically before reading each bit. And I'll go down here and define that subroutine. And the delay routine can basically just be a loop that loops a certain number of times to create a certain size delay. So we'll use the X register to count the times through the loop. So we'll push X onto the stack, and then we'll pull it off before we return from the subroutine. And then we need to load X with some value, depending on how many times we want to go through the loop. And then we'll create the loop and decrement X each time through the loop. and keep looping until x is 0. Question though is, how many times do we need to go through this loop to get to that 104 microsecond delay between each bit? Well, it's a bit more complicated because we can't just consider how long the loop takes. We have to consider how long all of the code that runs while we're reading each bit takes, and how long each of those instructions takes. So here's all the code, and from the 6502 datasheet, I was able to look up how many clock cycles each instruction takes. So the jump subroutine takes 4 clock cycles. The bit test takes 4 clock cycles. This branch takes either 3 or 4 clock cycles, depending on whether we are branching or not. So depending on whether we read a 1 or read a 0. And so actually our code path splits here. So that's why I've got these 2 columns. So if we got a 0, then we're not taking this branch. It only takes 3 clock cycles. We clear the carry flag, and then it's 4 clock cycles to jump down here to the receive done. And then the rotate is 2 clock cycles, decrement is 2 clock cycles, and then this branch back up to read the next bit is another 3 clock cycles, and then we start that over again. If the bit we're receiving happens to be a 1, then it's a little bit different. It's still 4 clock cycles for this subroutine to jump to the bit delay, 4 clock cycles to read the bit in, and then 4 clock cycles here because we've received a 1, and so we're jumping down here. So we don't execute these instructions. Instead, we just set the carry bit and would continue on. So what I did is I added 2 no-op instructions, and these 2 no-op instructions take 2 clock cycles each, and that kind of accounts for, or makes up, or sort of evens out the fact that here we have to do this extra jump, which takes 4 clock cycles when we go through this path versus when we go through this path. So if I add those 2 clock cycles, then that makes these 2 different conditions take about the same amount of time. So we can add all that up to see how much time that takes, but we also have to consider how much time we actually spend in our bit delay. So our bit delay subroutine that we just wrote, we've got 3 clock cycles to push X onto the stack, 2 clock cycles to initialize whatever our counter is going to be, and we need to figure out what that is. And then in our loop, the things, if we, however many times we go through this loop, each time through the loop, we decrement and we branch if not equal to 0. That in total takes 5 clock cycles. And then, of course, to return from the subroutine, we pull X back off the stack, and return from the subroutine is 6. So if we add all this up, depending on whether we received a 1 or a 0, is going to take 39 or 40 clock cycles. So very, very similar once I added these no-ops. Plus, depending how many times we go through this loop, 5 additional clock cycles per time through the loop. So if we've got 39 clock cycles plus 5 clock cycles per time through the loop, and we want that to equal 104 clock cycles because we've got a 1 megahertz processor, so conveniently every clock cycle is 1 microsecond. So 104 clock cycles is 104 microseconds. We basically just need to solve for X. And so 5x equals 65, x equals 13. So if we go through this loop 13 times, then every time through this whole bit receiving process, including this loop going 13 times, is going to take either 104 or 105 clock cycles, and each clock cycle is a microsecond with a 1 gigahertz clock. And so it'll take pretty close to 104 microseconds to receive each bit. And so let's set x here to 13. And that should ensure that we're taking right around 104 microseconds from when we get the initial start bit to when we read each individual bit. So that'll ensure that we're taking right around 104 microseconds from when we receive this beginning of the start bit and when we read each bit, and we read it every 104 microseconds. But that still is a small problem. We've got the timing between bits right, but if we're reading right at the beginning of the bit, we could be reading right on the boundary between bits. So if we're starting right when that start bit starts, 104 microseconds, we're reading right here. If we're just a little bit before, a little bit after, we're going to get a different value there. So what we should do is when we receive that start bit, we should wait half a bit time and then go every 104 microseconds. So we're reading in the middle of each bit. That way we don't end up reading on the boundary of a bit. So let's add a delay right here at the top, right after we detect the start bit, to wait half a bit time so that we're sampling mid-bit. And then that subroutine will be basically the same as the bit delay subroutine. So I'll just go ahead and copy that whole bit delay subroutine, make a copy, and we'll just change this to half bit delay. And it'll basically be just the same, except instead we'll wait for just half the time. So if we go back up, we detect the start bit here. We wait for half a bit time. Then we actually get in here, we wait for an entire bit delay before we read the first bit. So from the start of the start bit, we're actually waiting 1.5 bit times. So we basically skip the start bit and then read the middle of the first data bit, which is perfect. And then we loop and read the middle of each subsequent data bit. And as we read each of those bits, we rotate them into the A register. And once we've read all 8 bits, we print whatever's left in the A register as the character that we just received. And I guess if we want, we could add another bit delay here to account for the stop bit, though there's really no need to read it or check it or anything. Then we go back up and wait for another start bit. So let's give this a try. I'll assemble the program. Oh, we need to tell it -C02 to support the push X and pull X instructions, which are newer instructions. And I'm writing it to the EEPROM. All right, so let's pop the EEPROM back in. I'll reset. And now let's try typing some characters into the terminal program. And look at that. We're properly receiving, decoding, and displaying them on the screen. That's awesome. Obviously, we've only got data going one way, and as I alluded to earlier, there are better ways to do this, but I'll be exploring that in future videos. For now, I just want to thank all my patrons for helping to make these videos possible, and remind you that you can check out eater.net/6502 for more info, schematics, and data sheets. Or if you'd like to get a kit and try any of this out for yourself, I certainly encourage that.